In our last section, we talked about a French mathematician named Michel Rolle, and in this section, we're going to talk about another French mathematician, Augustin Louis Cauchy. And what you'll find is the French mathematicians were pretty solid for a pretty long time, and even today. But the idea is that we want to show a really interesting result that relates the derivative to the slope. So we kind of have this idea that the value of a derivative at the point is the slope of the tangent line. But there's an even more interesting result. And that result says that if a function is continuous on a closed interval and it's differentiable on the open interval with those endpoints, then there is some number c inside the interval where that the slope of the tangent line at that point is equal to the slope connecting the endpoints, or slope of the line connecting the endpoints. A visual example is here. If I have some curve and I take the endpoints and I draw a line through the endpoints, I get a slope. But what I find is that if the function satisfies the continuity and differentiability requirements that are here, that I can find at least one. And in this case, I found 2 points where the value of the slope at that point is equal to the average. And if you think about this, it makes total sense. Think about driving. If you drove from wherever, if you drove 500 miles in a car and you calculated your average speed as 40 miles an hour over the trip, well, I'm sure at some point you were going faster than 40 miles per hour, and at some point you were going slower or more slowly than 40 miles per hour, right? So you were going above the average and below the average. But there's got to be at least one point somewhere that you hit the average exactly, right? Because if at some point you were going 50 miles per hour and then at another point you stopped, well, at that point you would have had to have hit that number exactly. You would have had to have hit 40 miles per hour exactly. What you're seeing is this is kind of like the intermediate value theorem. And the intermediate value theorem talks about taking all the values in between 2 points. But you're seeing this related to the idea of derivatives. And what we can do is we can actually prove this using Rolle's theorem, but it requires a little bit more technicality than is probably appropriate for what we're doing right now. So we'll leave this as sort of a stated fact without proving it directly. Now, we can take this, again, we can take this form that has a derivative here and a slope here, and we can move this over and rearrange the terms, and you get this. F of b equals f prime at c times b minus a plus f of a. Why would I want to do that? Well, the reason I want to do that is because it has this obvious relationship to that point slope form of a line where f of x equaled m of x minus a plus f of a. Notice that b's have changed here to x's, and the f prime at c is now just an m. So what you're finding is that there's a strong relationship between this statement and this format and the idea of a general line. So these all kind of relate because we're talking about lines. Anyway, so we want to do an example. And a really good example, or a very simple but illustrative example, is this. I've got an object and I'm 230 meters above the ground. And I drop it, and I drop that object from 230 meters, and I can model where it's going to be in space by this function, negative 4.9 t squared plus 230. This models my position. So what I would like to do first is figure out what the average velocity is during the first 2 seconds. But if you're going to figure out the average velocity, all you're trying to do is figure out just the average rate of change. You're trying to say, all right, where did I end? Where did I start? What is my average velocity? So let's calculate this up. The first thing I want to do is I want to get my velocity function. So if I take the derivative of the position, you get negative 9.8 t plus 0. So what I would like to do then is get the velocity at 2 seconds, which is negative 19.6 meters per second. And I'd get the velocity at the beginning, 0 seconds, which is clearly 0 meters per second. And then to get the average, I take the differences in the velocities and divide by 2. So I get negative 19.6 over 2 meters per second, or negative 9.8 meters per second. So what that's going to do is that's going to at least give me an idea of the average velocity over this time period. Now notice that this is negative 9.8 because we are going down. We are falling, so going down. Now for part B, we want to figure out at what time point does the instantaneous velocity match the average velocity. So in this particular case, I want to know when the velocity is equal to negative 9.8. Well, I know the velocity is negative 9.8 t. So if I divide both sides by 9.8, if I divide both sides, let's see, this is 9.8 t, this is negative 9.8 meters per second. If I divide both sides by 9.8, I'm trying to get the units to match, but ultimately you're going to get that it's at 1 second, but I'm trying to figure out how that matches. And I'm actually coming up short here as to how those units are going to match. But ultimately, the answers you're looking for are just by getting these average velocities over the time period and seeing that at 1 second, it's actually right in the middle. Now, generally speaking, that won't be true. It won't be at 1 second. For something like this, it's going to accelerate even more quickly. So if I did from 0 to 3 seconds, I wouldn't expect that t equals 1/2 would be my value, but you'd have to plug it in to check to see whether or not that is, in fact, your average velocity.